slides.
Okay, let me see if I'm allowed to. Looks okay.
Oh, are you not given that permission? Just give me. No, I think you are a co-host. Yeah.
Yeah, looks okay.
Yeah, excellent.
You can see the slide.
So, yeah, we can see this. Can you just go to full screen? Yeah.
No, you probably this is probably the wrong one, right?
Oh, is
I
it?
have
Okay.
to share the other slide. Try again. The title should be Quantum Computing with Diamonds.
Quantum computing?
With diamonds and hopefully.
Yeah, so that's
still the wrong screen.
Yeah, it's on the screen. Quantum computing with diamonds, using and controlling individual electronic replacements.
And you see it full screen. All right. Okay. Yes.
Yeah.
Fine.
Yeah. Very good. So yeah, please, Dieter.
Okay. Well, thanks. It's a pleasure to be here. Almost as nice as being in Kolkata. And I would like to briefly start with an introduction of the people who did most of the work that I'm going to present. As you can see, most of the group is or was actually from India, although most of them have left now. I am starting with Jingfu Zhang, who's the only Chinese postdoc in the group. Then we have Koti, who's now a faculty member at Bennett University near Delhi. Swati is another postdoc from India. She recently joined a quantum computing startup here in Germany. Tanmoy is a postdoc was a postdoc from India, who's now working in Belgium. Harpreet Singh is still a postdoc from India. He works not on Diamond, but on a different project that I'm going to touch on briefly. And finally, there's also a German student in the group. His name is Alex Holberg, and he just finished his master's thesis on Monday. So I'm not quite sure what the background is of the people in the audience. So I have added one very basic slide, which tries to explain what quantum computing is about. And we always use the network model when we discuss quantum computing, which means we have a quantum register, which contains a number of quantum bits, hopefully quite many of them. And to actually compute something with that, there are three basic steps required. One, you have to initialize the quantum register. So you write the first information into it. And then you have to process it, which means you apply some steps over over a sequence which is defined by the algorithm that you're trying to implement. And each step implements a certain Hamiltonian for some duration tau, which generates a unit transformation of the data. And at the end, you read out the result, which you want to convert into classical information. So this is the very basic concept, and to implement that, we need, of course, as many qubits as possible. We have to be able to operate on each qubit individually or each pair of qubit, and we need a universal set of gate operations. That's the classical requirements for quantum information processing. Now, specifically, what I'm going to talk about here is about hybrid quantum registers. So while most implementations of quantum information process rely on a single type of qubit, be that now a trapped ion or a neutral atom or a superconducting circuit, I'm specifically interested here in combining different types of quantum bits into a single quantum register, with the idea that you can perhaps combine the good properties of them and avoid the bad properties of each of them. So in particular, as you have seen from the title, the system I'm interested in is diamond, which you all know. It's a pretty boring material in a way. I mean, it's very valuable, but it's pretty boring if you look at it, and the atomic structure, it just contains one element, which is carbon, and each carbon atom has the same environment, which consists of 4 identical carbons. So that's pretty boring, but we're not really using perfect diamond. We're using a more interesting variety where 2 of the carbon atoms are missing, and that one of them is replaced by a nitrogen atom, the second one by a vacancy, and together they form the nitrogen vacancy center or defect. And it's always these centers or defects which make the diamonds really interesting and valuable. All the colored diamonds contain different types of vacancies. Now, this specific one has been characterized extensively. If you look at the center, there are 5 electrons contributing to it, which together form a spin 1/2 state. And the photoluminescence of this center is shown here by this blue line when we excite, or blue curve, when we excite it with a laser at 532 nanometers. Now, we're not really working with this specific nitrogen vacancy, but we normally look at one where we have 1 additional electron, so it's a negatively charged center, which is normally called NV minus or just NV for simplicity. So in this case, you have a total of 6 electrons, which combine together for a spin 1/2 state in the electronic ground state. Now, to work with that, you need a very special instrument, which is called a confocal microscope. Confocal microscope basically consists of a laser that you direct on a microscope objective. So that's a lens with a large numerical aperture. So you get the tightest possible focus, typically a few 100 nanometers in diameter. If you then place the NV center in the focus of that laser beam, it will become excited and emit fluorescence photons. And the fluorescence photons, as you've seen on the last slide, are shifted to longer wavelengths. So when they hit this mirror, which is the so-called dichroic mirror, they are transmitted through the mirror while the green photons are reflected at the mirror. Behind the dichroic mirror, you place a lens, and in the focus of the lens, a pinhole. And the purpose of this pinhole is to get a depth resolution. So the microscope objective gives you a transverse resolution, and the pinhole, in addition, a depth resolution. So that allows you to get the minimal possible volume excited in the crystal, which is important to suppress unwanted signals. Behind the pinhole, you place a single photon detector. And if you scan this whole instrument over the sample, you get an image which typically looks like the one shown here, in this case for an area of 10 × 10 micrometers. Now, in the following experiments, we always work with single centers. So we're zooming into one of them, for instance, this one. And I will show you some results from one of these centers. Before I do that, I would like to briefly introduce the second system in which we have started to do experiments more recently, that's silicon carbide. Now, silicon carbide has a structure which it's not quite as boring as that of diamond, although very similar, and it's geometrically the same. You have atoms which are tetrahedrally surrounded by other atoms, The only difference is here you have two types of atoms, and every silicon atom is surrounded by 4 carbon atoms and vice versa. So there's a small change. The properties are still quite similar to diamond. You can make gemstones out of them, which look nice, and the band gap is quite large. They are hard, and you can have defects in them. And altogether, this is a less well-explored system than diamond, but it already has been shown that there are a number of interesting properties which may be useful for quantum information or sensing or quantum communication. In particular, the latter is an important difference to diamond because you can get photons in the telecom wavelengths, which is important if you want to implement quantum communication. Now, the main difference is because you have now 2 types of atoms, you have a much larger variety. You have 1 type of diamond, but for silicon carbide, already more than 250 so-called polytypes have been investigated. A polytype is a specific structure which locally is as shown here. But since this can be, since you have 2 types of atoms, the structure doesn't have to repeat every layer. So here you have a Z-axis, and along this axis you have different layers which are not superposed directly onto each other, and they are labeled here by the letters A, B, C. So the C layer on the bottom is different from the B layer above it, and so on. And if you have a single crystal, it means you must repeat the structure after a few layers, but not every layer. And for instance, in this case, where we look at the structure of 6H silicon carbide, you have 6 layers. Each layer has 1 silicon atom and 1 carbon atom. You have 6 layers before the structure repeats itself. So that gives you this large number of possible structures, and each structure can have several types of active centers, color centers, or defects. One of them that we are studying at the moment is the silicon vacancy, which is labeled V silicon. Again, we look at the negatively charged state, which has a structure shown here. It has a 3-fold symmetry axis along one direction, and you have around the missing silicon, you have, of course, 4 carbon atoms. So that's one type of defect. There are others which are often labeled for traditional reasons, V1, V2, V3, and so on. Now, if you take such a silicon carbide crystal, you can make it very pure, and then you can implant ions into it to create vacancies or color centers, which has been done here, for instance. This was implanted with a helium beam, and you see that we have on a grid pattern, we have different defects, and each of them can be studied and characterized. Now, we have chosen a few of them, for instance, this center here, which from the number of counts per second might be a single center. So we want to verify that, and to verify that it's indeed a single center, you can do a so-called anti-bunching experiment, which is more technically called the measurement of the second order intensity correlation function G2. What that means is you measure single photons, you record the arrival time, and then you do statistics as a function of the arrival time. Specifically, you check what the probability is to measure a photon at a certain time tau after the last photon has arrived. And if you irradiate the center, which was marked here with the yellow arrow, with an intensity of 10 microwatt, you get the curve shown here, which you can fit to the theoretical function shown here. Now, the important point is that for short delays, the probability drops below 0.5. And that is the sure indication that this is a single center, because when the center has emitted a photon, like a single atom, then it's in the ground state and it cannot immediately emit a second photon. It first has to absorb one, and that takes some time, and that's why this curve has a dip in the center. Not exactly at zero, because there are some inherent delays, but they are trivial. Now you can change the intensity, for instance, if you go up by about 2 orders of magnitude in intensity, you get the blue curve, which interestingly shows not only this anti-bunching peak in the middle, but also some bunching peaks next to it. And that can again be fitted. You need now a more complicated model for a 3-level system. And if you go through the math for that 3-level system, you can extract some interesting data from that curve. For instance, you find the probability of absorption, you can find the probability of emission or the lifetime of the excited state, and you can even find the rates with which photons are emitted when the system, or at the rate at which the system transits to this external state. Now, it turns out that if you irradiate this center with light, with sufficiently intense laser light, you can change, you can create spin polarization in the system. And then again, excuse me, that again allows you to study the center, for instance, by optically detected magnetic resonance. For the following measurements, we have chosen a different center, again marked here by this arrow. And what we do here is we irradiate it with a radio frequency and measure the change in photoluminescence intensity, or the rate change in the rate of emitted photons. And you get the curve shown here. You have the experimental data and the fit to that. The peak, the main peak here is at 72 megahertz, which corresponds to the zero field splitting between the ±1/2 and the ±3/2 state of this center. There's a second peak here, which comes at half the frequency, and that's actually an specifically interesting one. It means that at this frequency, 2 photons are absorbed from the radio frequency field by the single center. And you can verify that if you go to higher intensities. You see that this smaller peak grows actually faster than the large peak if you increase the radio frequency power. Anyway, this was just to show you a little bit what we're doing on silicon carbide. I would like to go back now to the more thoroughly studied diamond and then these centers. And this is a very basic talk that I'm giving here compared to the last one where you had some very hard theoretical discussions. Here I'm just showing some experimental details. So here is, for instance, a sketch of the setup for measuring on diamond centers. Very often we apply magnetic fields to lift degeneracies, and that can be done either by a bar magnet, a permanent magnet, or by an electromagnet. So that's this bar in the middle with the South Pole mark, magnetic South Pole. Then below it, we have this brown rectangle, which is a PCB board. On that PCB board, we have a microstrip line, and with a gap in between. In that gap sits the diamond, which you can see here. and then we draw a thin wire across the diamond, which is used to apply radio frequency and microwave fields by running a current through that wire. So that is the basics of the setup. Of course, there is a lot of optics in addition to that for generating laser pulses. There's a lot of electronics for generating the microwave and radio frequency fields. So this is a typical situation, by the way. What most people do, we put the wire over the sample and apply current through it. We've recently shown that you can also use a resonator, which has the advantage that it has a larger volume over which you can get good excitation of the center, and the resulting fields are about an order of magnitude stronger than with the wire. Now, how does such an experiment work? What you have to do to use that system for quantum information processing? Let's start with the level system. Electronic ground state, that's this triplet A2 state, as splitting in the absence of magnetic field between the MS equals 0 state and the plus and minus 1 states. I'll come back to that splitting in a moment. The same holds for the electronically excited state, where the splitting is about half the size of the ground state. Now, if you want to work with that, you have to excite it with a suitable laser. Normally, we use a green laser at about 2.2 electron volt, and that means the system is excited into the continuum or vibranically coupled states above the electronic ground state, but they relax very quickly to the vibronic ground state of the electronically excited state. Now, this transition, the absorption of the photon and the emission of the phonons, is spin conserving, ideally. That means if the system is initially in the MS equals 0 state, it will go to the excited MS equals 0 state and back without changing. Now, this is a first approximation. If you look more closely, you will find that in addition to this triplet manifold, the system has, of course, a singlet manifold where the total spin is 0. And the system has a certain probability of crossing over from the triplet into the singlet manifold. And this probability is higher for the MS equal plus and minus 1 states than for the 0 state. So the system has a certain probability of crossing over. It will relax inside the singlet manifold, not giving off any radiation, and eventually come back to the triplet manifold. But when it comes back, it has a certain probability to end up in the MS equals 0 state, while it was originally in the plus and minus 1 state. The MS equals 0 state will always stay in MS equals 0, but if it cycles through the singlet manifold, the plus and minus 1 state can also go to 0. And that means if you repeat that experiment often enough, you end up with all the population in MS equals 0. So you have initialized the system into the specific state, which is one of the requirements that we have for quantum information processing. In addition, this cycling through the singlet state takes some time, and during this time, there is no photon emitted. So that means overall, if you're initially in the MS equal plus or minus 1 state, the system will emit fewer photons than if it's originally in the MS equal 0 state. And the result is that the total number of photons that you scatter from a single center depends on the spin state. And that's, of course, one possible way to read out the spin state of the system. So you count photons for a certain period, and if the photon number is low, then you conclude that this is the MS equal plus or minus 1 state. If it's high, you conclude it's the MS equal 0 state. Now, these two states are different in terms of energy, and the energy difference between them in zero magnetic field is about 2.87 gigahertz. If you apply a magnetic field, then the degeneracy of the plus and minus one states is lifted, and you have two allowed spin transitions that you can excite with microwave fields, which couple to the transverse spin component Sx and Sy. So if you choose, for instance, two of these energy states or energy levels as quantum states, basis states for a quantum bit, then the microwave pulses allow you to generate unitary arbitrary control operations on that spin. You can represent them by rotations on the Bloch sphere, like for every two-level system. That applies here also, and you can change or control the direction of this rotation axis by the experimental parameters of the microwave pulse, like frequency, amplitude, phase, and duration. So you can control the orientation, you can control the duration of the pulse, and that means you have arbitrary single qubit operations. And similarly, you can check, of course, 2 qubit operations. That works in principle also, but there is a catch to that. Let's first look at the electron spin. So you want to apply a single qubit operation on an electron spin. For that, you initialize it, and that means you put all the population in the ground state, ms equals 0. Then you apply the gate operation, which is in our case a microwave pulse with variable duration. And at the end, you again read out the population of the ground state, of the zero state. This population depends now, for instance, on the gate duration. And you see here one example where it oscillates between the 1 and the 0 state. These are logical states, not spin states. Now, these oscillations are known as Rabi oscillations, and they correspond to different gate operations. If you apply just a sequence of pi pulses or a single microwave pulse of long duration, you will see that the populations of the state oscillate with a certain frequency, which we know as the Rabi frequency. Now, this is an example where we deliberately reduced the microwave field strength, but applied rather long pulses. And you see that the coherence in the system, although you have this long microwave pulse, remains very high over several hundred microseconds. So that means we have here a system where we can generate single qubit gates with very high fidelities of more than 99%. So instead of applying one long pulse, you can also apply 2 short pulses. In both cases here, we assume they have a flip angle of pi/2. What can that be used for? Well, if you have first polarized the electron spin by the first laser pulse here, then applying a microwave pulse means you're creating coherent superposition of 2 spin states. If they then evolve, then you get the so-called free induction decay. The second microwave pulse converts part of this evolving coherence back into population of the state, which you then read out during this laser pulse here. So if you do that as a function of this time t here between the 2 microwave pulses, you end up with this blue curve, which is often called a free induction decay according to standard NMR experiments, or in optics it is known as a Ramsey fringes experiment, because in optics, like Ramsey discovered, you can measure such an FID by applying the second pi/2 pulse and reading out populations. Now, in most cases, I assume this blue curve is not what you were looking for when you started to do quantum information processing. And it's not so straightforward to interpret. However, it shows, first of all, that our single center is not really a spin 1/2 system. And to get more insight, it is a good idea to apply a Fourier transform operation as was done here. And the result is a spectrum which apparently contains 6 different resonance lines. Now here it becomes relatively easy to interpret the spectrum. And it turns out that in addition to the electron spin, you have, of course, always a nitrogen nuclear spin, because the 2 relevant isotopes are N14, which is more than 99% abundant in natural abundance. And in addition, diamond, of course, contains carbon. Now, carbon atoms are in most cases carbon-12, which don't have a spin, but there is a certain percentage of carbon-13. In natural abundance, this percentage is about 1%, and you can choose what type of crystal you need, either with lower or higher carbon-13 content. Now, how far those carbon-13 spins are from the electron spin is, of course, a matter of chance, because the carbon-13s are randomly distributed in the crystal. Now, if you analyze the spectrum, you can at least determine the coupling strength, and you can actually use these nuclear spins in addition to the electron spin as quantum bits. And in some cases, you have not just a single carbon, you can have multiple carbon atoms, so you can have multiple qubits. So in this example, we had one carbon which has a hyperfine interaction of 8 megahertz. There was a second carbon-13 with 5.8 megahertz hyperfine interaction. Then we have the nitrogen-14 with about 2 megahertz, and a third carbon-13 with less than half a megahertz of hyperfine interaction. So in principle, all these nuclear spins can serve as qubits, and that's what I mean with a hybrid quantum register. What we have to learn when we work with such a system is how do we control it. That is not quite trivial, and I don't have time to discuss all the details, but what I can do and what I would like to do is to show some of the issues and some of the solutions that we have developed for them. First of all, as always in quantum information processing, you need to initialize the system. Initialization means that you have to set the system into a specific spin state. For instance, you would like to have both spins in the ground state. Here we have a partial system where we have chosen 2 of the electron spin states to serve as 1 qubit, and 2 of the nuclear spin states to serve as the second qubit. If you want to initialize that, you start normally with a system in thermal equilibrium where all the 4 levels have equal populations. If you then apply a laser pulse, you polarize the electron spin, as I have discussed before, and the laser pulse does not affect the nuclear spin, at least not to first order. So the result of the laser pulse is a polarized electron spin, but a completely random nuclear spin. So this is a mixed state, which is not ideal for quantum information processing. However, you can turn it into a pure state by combining the laser pulses with microwave and radio frequency pulses. because of the hyperfine interaction, the two electron spin transitions in this system are not degenerate. So it is possible to apply a resonant microwave field on one of the transitions, which flips the corresponding spin from the ground to the excited state. And then you can drive this nuclear spin transition between the one down and one up state to invert that transition. And what you have now is, if you take that together, we have a completely polarized nuclear spin. You see the nuclear spin represented by the arrow is always in the spin up state now, but the electron spin has been depolarized. It's now equal probability in 0 and 1 state. So if you want to get our polarized system, you have to apply a second laser pulse, which takes the system back down to the ground state. So we do two things basically. We combine laser pulses with radio frequency pulses. The laser pulses remove entropy from the system, while the microwave and RF pulses conserve entropy. They are unitary transformations. And if you take that together, we have a polarization of the electron by the laser pulse. Then the two unitary operations generate a swap operation between the electron and the nuclear spin. And then I want to discuss a bit more details about the second laser pulse, which is supposed to bring this system where we have now the full spin system with 3 nuclear spin states and 3 electronic spin states, where again the electron spin is completely depolarized, but the nuclear spin is completely polarized. So again, the laser pulse is supposed to take that to a pure state by bringing the spins from the plus and minus 1 to the 0 state. So that's what it's supposed to do. Let's see what it actually does. We measure here the population of the target state, so that's the 0, 0 state, as a function of the laser pulse duration. Before the start of the laser pulse, all 3 electron spins had equal populations, so the initial population should be about 1/3, and ideally the laser would bring that to 1. So that's what we would like to see the laser do, drive the system from 1/3 to 1. Now, what's really happening is shown here by the blue symbols. First of all, the population increases. That's closely along the ideal line, but then it goes through a maximum and decreases again. So what's actually happening here is that the laser pulse has some depolarizing effects on the nuclear spin. This is not wanted and definitely was not foreseen, but it makes sense in the end, as I will try to explain in a moment. But this picture where we have a polarizing effect on the electron and a depolarizing effect on the nuclear spin needs, of course, to be verified. And the way to verify that is to measure also the population of the other spin states, particularly the Mi equal plus and minus 1 states of the Ms equal 0 state. If we do that, you see here the red and black symbols. Those populations start at 0, but as we apply the laser pulse, they rise. And after a long enough laser pulse, the system is completely depolarized as far as the nuclear spins are concerned, with all of them at about 1/3 population. So this is unfortunately a result that we didn't plan. The laser depolarizes the nuclear spins, not completely. You can still work with that. You get a pretty decent polarization or population of the target state, but it's not unity. And you can, of course, check what the mechanism is or consider possible mechanisms. The main issue is that as you're applying laser pulses, you're changing the electronic configuration of the center. You have intersystem crossing, so the spin state goes, in the case of diamond, from 1 to 0, from the triplet to the singlet. In addition, you can have ionization processes. That is, you go from NV0 to NV minus or from NV minus to NV0. In all cases, the electronic structure changes, and that means that the hyperfine interaction with the nuclear spin is modulated. So that creates basically noise on the nuclear spin, which leads to depolarization. Now, one possible solution for that, or partial solution, is that to optimize the photon energy for this excitation. And how that can be done, you can understand if you look at this level scheme. We have, of course, the valence and the conduction band. In diamond, they're about 5.5 electron volts apart, and the NV minus sits somewhere in the band gap, with an energy level splitting of 1.95 eV. Now, if we drive this transition of the NV minus with a green laser, we can, of course, populate the ground state, but we can also cause ionization. So the green laser, for instance, by 2-photon absorption, can induce a transfer to the NV0 state by taking away the additional electron. Now, the NV0, of course, has a different energy level scheme, but you can also drive the NV0 back to the NV minus by again adding an electron. And as it happens, this can again be done by 2 photons from the green laser. And that's the cause of the modulation, or some of the modulation. If we want to avoid that, we have to stop this ionization dynamics. Now, it's difficult to stop that completely, but you certainly can reduce it, for instance, by using an orange laser. The orange laser has lower photon energy, which means that it can actually excite NV or ionize the NV minus or deionize the NV minus and drive it to NV0, but the system will not go back, and therefore you stay with NV0, which is basically invisible to us, so it does not contribute to the depolarization that we have. Now, I notice I'm using up too much time, so I would like to skip a few slides and come to this issue of the hybrid system control. And what we're trying to do is to make best use of 2 or more different types of qubits, for instance, the electron spin and the nuclear spin. And if you want to optimize that, you have, of course, consider both their properties, their strengths, and their possible weaknesses. In particular, the electron spin is always required because it's the only way to polarize the system, to initialize it, and to read out the resulting spin state. That goes through photons, which couple to the electron, but not directly to the nucleus. In addition, the electron has the nice property that it has a relatively large dipole moment, so it reacts quickly to external control fields. The nuclear spin, on the other hand, has a much weaker dipole moment, which makes it slower, but slow in every respect. For instance, the dephasing times of the carbon-13 or the N14 are very low. So this is an ideal system for storing information. In addition, of course, you have quite many of them. Now, the control of the electron spin, I've already discussed. You apply microwave pulses. In principle, you can do the same for the nuclear spins, except that the resonant AC fields are here in the radio frequency range, So you apply radio frequency pulses. And they can be resonant with specific transitions. And in the case of the N14 spin shown here, you have in each electron spin multiplet, you have two different transitions. Each of them has a known transition energy or transition frequency, and that allows you full control. So in principle, that works. Well, the fact that it works, sorry, that I went back instead of forward. So in principle, that works, but there is, of course, always a but. I mean, the issue is these different interaction strengths, they can cause a problem because also the electron spin reacts quite quickly, the nuclear spin quite slowly, but the electron spin also dephases if you wait too long, and sometimes the gate operation on the nuclear spin is too long. I'll show you that in an example. Here we want to do a 2-qubit gate operation with the nuclear spin as the target qubit. To do that, we first excite the system into a superposition state by applying a laser pulse and a microwave excitation pulse, which generates a coherent superposition of two electron spin states. Then we apply a radio frequency pulse, which necessarily is rather long compared to the microwave pulses, which drives the nuclear spin. Now, as a function of this pulse duration, we expect, of course, some kind of Rabi flopping for the nuclear spin. So you would expect ideally to get such a sinusoidal signal on the nuclear spin as we have seen it on the electron spin before. However, if you do the experiment in a typical situation, you will not get this oscillation, but just a decay. And the reason is essentially time scale. You see here the time scale of this radio frequency pulse is on the order of hundreds of microseconds. And that's dictated by the interaction strength of the nuclear spin. If you want to do a pi pulse, for instance, you need on the order of 50 or more microseconds. And the dephasing time of the electron spin, on the other hand, is on the order of some tens of microseconds. And that's why the signal decays here before the operation on the nuclear spin has happened. Now, it turns out there are a number of possible solutions. For instance, you can use so-called protected gate operations. You can apply rephasing operations to the electron spin. Here is the so-called dynamical decoupling scheme, also known as spin echo experiment. And if you do that to reverse the dephasing of the electron spin, you get an almost ideal operation as shown by these red circles here. So that is possible. You can go further, but there are some other issues. In particular, these radio frequency fields that you apply, they also affect the electron spins, and we found that that can be a serious problem. Also, if you want to control the nuclear spins, so the gate operations that you get are quite long, and you have to apply radio frequency field in resonance with all the possible transition frequencies, which may be extremely difficult or even impossible in some systems. And because driving the nuclear spin requires relatively strong radio frequency fields, they also affect the electron spins, which are, of course, not resonant with the transition, but if the field is strong enough, it can drive the electron system even more effectively than the nuclear spin. So these are serious problems that you have to consider. It is possible to solve them. Of course, I don't have time for all the details, but I've already shown you this possibility of refocusing, which can also remove some of the other issues. But the nicest solution, in my opinion, is to do experiments without radio frequency field. And this is possible because of the hyperfine interaction between the electron and the nuclear spin. There are a number of options. I would like to skip the first option here to save some time and just discuss the second one, which we call indirect control. The basic idea is the following. Let's assume we have a carbon-13 nuclear spin. For the isolated spin, of course, the quantization axis of the spin is along an external magnetic field. In the presence of the electron spin, however, it's different. In addition to the interaction with the magnetic field, you have the hyperfine interaction, which can also be considered as an effective magnetic field acting on the nuclear spin. Now, this magnetic field or hyperfine interaction also has a direction, and that direction is in general not along the axis of the magnetic field, but at some angle to it. And fortunately, it is very easy to invert this interaction, because if you flip the electron spin, for instance, from the +1 to the -1 state, then this field direction actually inverts. And so the total effective magnetic field acting on the nuclear spin, shown here by this black arrow, can change direction and amplitude if you just apply microwave pulses to the electron spin. And if you do that, then the effective field is not along the spin, so it precesses around that axis. You see here some of these oscillations. And it turns out that by combining several such rotation periods in a pulse sequence, you can get universal control of the system. So you design a sequence with suitable microwave pulses with certain durations, flip angles, amplitudes, and phases as necessary. You can drive your nuclear spin system, here shown on the bottom by this black arrow. And if you excite the electron spin, you change the orientation of the quantization axis, it precesses around that, and overall you get this beautiful control operation, which you can use for quantum information processing, for instance. Now, again, for the sake of time, I'm going to jump over a few of the slides and just show you that while this may seem relatively complicated, it is actually extremely efficient. And for this, I would like to discuss the so-called quantum speed limit. This is a general question: how fast can you drive a quantum system? What is the shortest possible time for a certain gate operation? And this is actually very easy to answer if you know the strength of your interaction. For a spin, the strength of the interaction is given by the Larmor frequency, or the interaction strength, and the shortest possible single qubit gate, so not gate, for instance, is given by pi over the Larmor frequency. In the case of a 2-qubit system, well, you can choose either the electron spin as the target qubit or the nuclear spin. In the case of the electron spin, everything is easy. The system operates fast and you don't have to worry. However, if you target the nuclear spin, the problem is that the radio frequency fields are too weak if you combine them with the low gyromagnetic ratio of the nuclear spin. So if you want to have a fast gate operation, you first have to check what the strongest interaction is. And in that case, that's the hyperfine interaction. For a specific pair of spins, we have a hyperfine interaction of 110 kilohertz. And then you can calculate the quantum speed limit for that case. You get about 4.54 microseconds. So let's see what happens if you do this experiment. Again, I mentioned no radio frequency field. We only use the hyperfine interaction and microwave fields. You can use the electron spin as the control. Here we have it in the active state. So we get oscillations of the nuclear spin. And if you look at the evolution, you find that to flip it from the logical 1 to the logical 0 state, you need 4.54 microseconds, which corresponds to the quantum speed limit. So we can actually saturate the quantum speed limit in that system. Yeah, this is just proof that the whole system works by some quantum state tomography at the end. So let me come to the conclusion. What I tried to show you is that we can do quantum information processing with different types of spins. So that's great, but in any case, you might want to ask, or some people want to know, can it also be useful? I mean, of course, we know that, and this is more general, not just for nuclear spins or so, but we know, of course, there are some quantum algorithms where quantum systems can beat classical computers like the Grover algorithm or Shor's algorithm. Now, I'm not sure how many people really want to use quantum computers for analyzing data banks or factoring large numbers. But there are some applications which are really useful in my view, particularly for physicists or chemists. Quantum simulations are a prime target, and they have actually been around for quite some time. For instance, we have used a nuclear spin system some time ago to study localization. You see here, we start with the quantum state, which is initially localized on a single spin. So the vertical axis is the size of the state in terms of number of correlated spins. The horizontal axis is time, and you see, of course, the system is spreading. Now, you can, if you just let it spread freely in the absence of any perturbation, it will actually become bigger and bigger, and the system is completely delocalized. But we also know that many systems are in practice localized. That has been studied, for instance, by Anderson, and that's known as localization. And we can simulate that in a quantum computer or quantum simulator. You see here that the spreading is much slower, and it actually reaches a quasi-equilibrium state if you add a certain perturbation. I don't have time to discuss that in detail, but we chose a perturbation where you can change the strength. And in this case, you get, as a function of this perturbation strength, a very clear-cut signature of a so-called quantum phase transition. You see a critical behavior. For weak perturbations, you have a delocalized phase. For strong perturbations above the critical perturbation strength, you have a localized phase where the system doesn't grow without limit. So this was done with a relatively large quantum register of a few thousand nuclear spins. This was a quantum simulator because we didn't have individual control of the qubits. You only can apply or generate a certain Hamiltonian. And if you're still not satisfied that quantum simulations are something which may interest many people, I have here a real killer application. I mean, we know that the internet transfers most of its data actually in the form of images or movies or so. So if you want to process movies or images, you need, of course, a lot of number crunching capabilities. And it turns out you can also improve that by quantum computers. I have here a simple image, and if you want to operate on that, you apply some mathematical transforms like this hard transform here. And these mathematical transformations are normally implemented as matrix operations. So to do that, you first have to encode your image in the form of a matrix. Then you apply your math operations. That's a processing step. And finally, you decode it by bringing the matrices back to pixels. So if you do that on a classical computer, you need essentially a number of bits or bytes, which is equal or proportional to the size of the image. So for instance, you may have 16 megapixel from a mobile phone, then you need 16 million pixels or bits for a black and white image, and correspondingly more for a color image. Now it turns out you can also encode it on a quantum state, and then the number of quantum bits required is only a logarithmic quantity of the number of pixels. And of course, the operations are also correspondingly faster. Let's look at a very simple operation like finding a border between two colors. So here you want to find the border between the black and the white regions. And doing that on a classical computer requires, of course, to compare roughly 16 million pixels, well, a bit less on this image, but if you want to do it on a real one, you need more. So you want to compare each pixel with its neighboring pixels. Turns out on a quantum computer, when you have encoded it in a quantum state, you only need a single operation on a single qubit, independent of the size of the image. So that is much easier, much faster than any classical computer. Now, this potential and these demonstrations of possible advantages have been recognized by government funding organizations for 20 or 30 years. But as the demonstrations became more convincing, also industry has started to pour money into this kind of technology. You see here just an overview of some of the funding which has flown into quantum technologies over the last 10 years or so. And as a result, many startup companies have jumped up, which generate hardware for quantum information, software, other components, so application software, or we have these so-called full stack companies, which are mostly the large industry giants like Google and Microsoft, which generate full usable computers and services. And of course, there are many more that I didn't show here. Okay, well, I think I have to come to the conclusion. I tried to show you that computers based on quantum mechanics may be qualitatively more powerful than classical computers. It's sometimes not so easy to implement that. Particularly, I have focused on so-called hybrid quantum registers, which combine different types of quantum bits that has some advantages and create some challenges. And we're hoping to overcome most of them. I also tried to show you some interesting systems, including Diamond, and I would like to thank you for your attention. And of course, I'm happy to take questions.
Thank you very much, Professor Dieter. So I think there is a question in the chat box. Subhashish Parikh, maybe you can unmute yourself and ask.
Yeah, thank you. So thank you for the talk, Professor. My first question is, are there any correlation among the nuclear spin frequencies that you showed in slide number 20?
Okay, let me jump to that slide.
Sorry, Dieter, it seems like you have not, I mean, the slides I don't see. Maybe they have been unshared.
Yeah, I stopped sharing, but
okay.
I'm coming back. So you were talking about this slide, right?
Yeah.
Sorry, can you repeat the question then? You asked about correlations?
Yes, yes. Just wondering if there are any correlations between these peaks.
Well, correlations in the sense that the frequencies are not independent of each other. That's why what I'm trying with these bars on the top, because, for instance, the hyperfine interaction of 8 megahertz means that the pattern must repeat itself after 8 megahertz. Or you have the smallest interaction, smallest hyperfine coupling, which is 0.4 megahertz. And so you see the two peaks here are 0.4 megahertz apart. And these are again 0.4 megahertz apart and so on. So does that answer your question?
Yeah.
So I mean, if you combine all these different hyperfine interactions, you get essentially the pattern shown at the bottom.
Thank you. Secondly, just asking what kind of readout system you use, particularly what kind of detectors and amplifiers read out your NV-based quantum systems.
So the detector is a single photon counting avalanche photodiode. In the case of diamond, it's a silicon based photodiode. In the case of silicon carbide, we're actually using another detector which is more sensitive to longer wavelength photons. But in each case, the detector just generates pulses, which each pulse corresponds to a single photon, and those pulses are then counted by a counter which converts the arrival time into a digital number. Then you add these photon numbers, so the number of pulses for the duration of the laser pulse. Typically, we have, in the case of NV system, you have a count rate between 50 and 100 kilocounts per second. For the silicon carbide, it's a bit lower, around 10 kilocounts per second. So you calculate or you count for a certain duration, and depending on the number of photons, you decide if this spin was originally in the ms equals 0 or the ms equal 1 state.
Right. Thank you, Professor Dieter.
Thank you. Are there further questions? Dieter, I was actually curious about the localization transition which you showed towards the end.
Yes.
So is that something where you have a one-dimensional array of NV centers which are already interacting and showing these kind of localization transitions?
No, this is the system that we're using here are nuclear spins, no NV center. This is actually an ensemble quantum simulator. Oh. And the way to do the experiment is you start with a dipole-dipole Hamiltonian, but then use that just as the starting point for generating an effective Hamiltonian, which is a Hamiltonian that connects pairs of nuclear spins. And with, I don't know, you're certainly familiar with that. So you have so-called flip-flop Hamiltonian, which drives transitions where the total angular momentum is conserved. And that creates correlations between neighboring spins, and we just follow these correlations. It correlates more and more remote spins, and that's this spreading that you see here.
And the localization, would you put that down to a many-body localization? Is it actually a disorder-driven one, or?
Yeah, that has been a long debate, and I don't have a convincing argument if it's. We suspect. I mean, it's a simulation experiment. So you map the system that you're trying to simulate onto the system that you realize in the quantum simulator.
Yeah.
And whether you map it to, I mean, you could probably map a single particle localization or Anderson localization onto this simulator, or you could equally map a multi-particle localization model into that. So I don't think I can give a convincing answer to that.
Okay, fair enough. And since you are on this slide, what is your take on, can it be useful? I mean, yeah, it can be useful for quantum simulations. I understand that. But for more standard quantum information tasks, is this something which we are going to see as a competition to superconducting junctions and so forth?
You mean the NV system?
Yeah.
Yeah, I hope so, but I'm definitely not sure. I mean, in terms of the physics of the NV system, it would certainly be possible. But to make it actually take off, and some of the companies that I have shown are actually betting on that. So they are offering commercial quantum computers based on NV systems. The problem is, at the moment, it's only possible to work with single centers. And if you want to have a commercially viable quantum computer, you will have to create interactions between these centers. And that is in principle possible. There are known solutions for that, but there are huge challenges involved, which are not fundamental physics, but engineering problems.
I see.
And this is not I'm definitely not an expert on engineering these systems. So I don't think I should make a prediction on that part. I can definitely say at the moment, there are no known obstacles which would prevent it, but it will be a large challenge.
Thank you very much for that answer. Yeah, so thank you for the talk again, Dieter, and sorry to have missed you by one day, but I think this entire meeting is online. I'm sitting in Chennai, away from Kolkata. So, so thank you very much, and we conclude this